I don't know. There we go. All right. Hi. We're about to get started. Can someone towards the back of the room close the doors? That's the plan. Have blue sheets been started?
Yes.
Yes.
Yes,
all right.
they have now.
Okay.
I passed them out.
Good. Does somebody want to take minutes? Can we get a volunteer to take minutes? Thank you. All right. Yes, that was Matt.
Oh, perfect.
You may have noticed that neither of us is Allison. She's had to stay home to deal with the family situation, so we're sitting in for her. So your indulgence is, consider it begged for. Okay, if you've been here before, you recognize this. If you haven't, you might not. This is essentially the IPR policy. We're under substantially the same IPR regime as the IETF, but there's some minor differences. So note well. More policy. There's going to be a lot of photography here today because we've got our ANRP winner. No? Matt? No photographs. Okay. Skip that. Ignore that. So, yes, so no photographs. Right, and for research group chairs who are meeting later this week, please don't forget to include the note well in your slide sets. For those who aren't familiar with the IRTF, the mission is to focus on longer term research issues related to the internet in parallel with the IETF. They focus on engineering and standards making. We focus on research. We're organized into topical research groups, which are parallel to, in some cases, but different from working groups, IETF working groups. Instead of having an IESG, we have an internet research steering group. It's mostly the research chairs and a small number of at-large members, including Spencer. Right, so we do not produce standards at all, period. We do produce documents, some of which may be published as RFCs, and those will be experimental or informational. Okay, these are our research groups. These are all probably familiar. There are a couple of changes from the last time we met. One is that DINRG is now a full research group. We've been promoted. And there are two new groups meeting for the first time as proposed research groups. One is privacy enhancement and assessment, and the other is the quantum internet research group. everybody's meeting except ICCRG this week. Today's, excuse me, today's agenda. As I mentioned earlier, unfortunately, Allison is not with us. A couple of things are coming up. ANRP for 2019 nominations are due November 11th, so get those in. We're only going to have one ANRP presentation today due to last-minute visa issue, but there'll be news on that. The talk that we're going to have today, you've probably heard about it in TLS and other working groups today. Johanna Aman is going to be talking about, excuse me, HTTPS deployment metrics after DigiNotar. So it's an updated version of the IMC 2017 paper with new data. Cats. Allison's, yes. Okay. Sometimes people confuse ANRW and ANRP. So Allison provided a slide disambiguating the ANR things. The Applied Networking Research Prize, it's an annual call for nominees based on papers that have already been published elsewhere. The Applied Networking Research Workshop, of course, is a workshop with an annual call for papers, both already published and not. And then presentations are given in a day-long workshop co-located with the summer IETF. This year, it's going to be in July in Montreal, or I should say in 2019. Okay, so we're done, and if there are no questions, let's see if we can get out of this. Escape doesn't get us out of this. But yeah, Johanna, you're up. As soon as we can figure out how to switch the slides. I saw a menu. Oh, okay.
Thank you.
Yeah. Yeah. Okay. I can. This one, yeah.
Yeah, we can move this in there.
Yeah.
Okay.
All right. And then here's the.
Hi.
Okay. Is this on? Yes. Hello, everyone. I'm happy to be here. Thank you for the introduction. So my name is Johanna. I am a researcher at the International Computer Science Institute, which is a research institute that's affiliated with UC Berkeley. And as you can already see by the slashes, I wear several hats. I am simultaneously also an engineer at a startup called Corelight, and I'm affiliated with the cybersecurity department at the Lawrence Berkeley National Laboratory. And today I'm going to give a talk that is called Mission Accomplished HTTPS Security After DigiNotar. That is a paper that was presented at the Internet Measurement Conference last year. And later, I'm also going to talk a little bit about additional work that was done later that kind of ties into this research too, and is also about TLS. 1 second, mouse pointer. This work was done together with a few other people at the Technical University of Munich and the University of Sydney. And one thing before I start, so this setup is a little bit different than what I typically have, because typically I can see the next slide too. This presentation is a little bit long, and if I am confused a little bit, confused a little bit sometimes, it might be because I actually am, because I have no idea what's coming up next, because I have a lot of slides to go through. Okay, let's start a little bit. So what is this paper about? So basically what we did in our paper is we said, after the DigiNotar incident, what did change? And more specifically, we took a look at the TLS and HTTPS security extensions that mostly came up after DigiNotar. And we were interested in how deployment actually looks like in practice. And we picked a few extensions that we thought were the most important ones. More specifically, we looked at certificate transparency, HTTP strict transport security, HTTP public key pinning, the TLS fallback signaling cipher suite value, certificate authority authorization, and day in TLSA. And how did we look at this? We did active measurement and passive scans. So active measurements means that we basically did domain-based measurements of the internet on port 443 from 2 continents. For this, we amassed the, at that point, largest domain list that was known to us and scanned for more than 192 million domains. I think we even scanned a few times, not just once. And we also did a passive measurement on 3 continents. So we had 3 sites at which we got access to the internet uplink of universities. And where we looked at the outgoing TLS connections and looked how certificate transparency was used there. And one thing that was, from my point of view, scientifically interesting about this work is that we had an active, a shared pipeline between the active and passive scans, because in TLS, in academia, a lot of scans have been done before, both active and passive, but they typically, even when they were done simultaneously for the same paper, did not, it was completely different software, that is the active part and the passive part. And in our case, what we did is basically, for the active scans, we took a network trace of the entire traffic that was exchanged by the machine that was doing the scanning and shoved that trace through our passive measurement pipeline later, where it was possible, and then used the data from the passive measurement pipeline. So we had the exact same source code running for both the active scans and the passive measurements later. Okay, I hope I'm not boring too many people of you here, because at first I'm going to give a short introduction of certificate transparency for those people that do not know what it is. So the big idea behind certificate transparency is that it would be neat to have basically an authoritative list of all the certificates that are being used and trusted on the internet. And the way that certificate transparency uses to make this list available is that you have semi-trusted log servers, and those semi-trusted log servers basically give out inclusion proofs when a certificate is added to them. And such inclusion proofs can be presented to the browser, and the browser can verify that a certificate has been added to a log server. And the end game of all of this is that you only accept certificates as valid if they are included in certificate transparency, which Chrome started to enforce, I think, in April this year. Back when the paper was written, this was not yet being enforced. So, and basically we have 3 big entities that are interested here, which are the certificate authority, the certificate log, and the browser. And as you might also know, there are several ways in which certificate transparency can be used and in which those inclusion logs can be transferred to the client. The first, potentially easiest to explain method is that you as a user request a certificate and get the certificate from the CA. And if you want to give out a certificate log, an inclusion proof of certificate transparency, what you can do is you can send that certificate to certificate transparency. Certificate transparency will send you back a signed certificate timestamp, so the inclusion proof. And when a web browser connects to you that supports certificate transparency, you can send the proof in a TLS extension. The second way that you can do things is that the CA basically sends the information to certificate transparency. In this case, the CA sends a pre-certificate to a certificate transparency log server, and a pre-certificate basically is just the certificate with an additional extension that says that it's not valid, so it has a poison extension. The certificate transparency log signs this and sends the signature back to the CA. The CA takes the signed certificate timestamps, includes it into an extension, puts it into the certificate, and sends the certificate with the pre-certificate SCT to the web server. And the web server doesn't have to do anything besides sending that certificate to the browser. And a browser that supports certificate transparency basically does the reverse process. It gets the SCT out of this, removes the extension, and then checks if the SCT validates against the certificate without the extension. And there also is a third way of transferring the proof that's a little bit esoteric, which is that the CA creates the final certificate and sends the certificate both to the web server and to the CT log. The CA gets back the SCT, and the web server supports OCSP stapling in this case. And the web server gets an OCSP reply, and the current OCSP status every few hours or days from the CA. And when the browser requests the certificate and signals that it supports both certificate transparency and OCSP, the SCT is sent in the stapled OCSP response that the web browser can then use to validate the status again. So we basically measured how much we see certificate transparency being used in practice. And so these are numbers from 2017, so these are a year old by now. And back then you could see that approximately, let me cheat a little bit and look, that approximately 10% of domains and 7% of certificates were part of certificate transparency. We did a follow-up paper this year, which will be presented tomorrow at the Network Measurement
NMRG. Yes.
Research Group, I think. Today, after Chrome started enforcing certificate transparency, things look a little bit different. In that measurement, about 68% of certificates actually had an embedded SCT. So the ecosystem has changed a little bit. However, what's a little bit interesting is when you look at the passive measurement side, because when you look at passive measurements, this is again the results of a year ago. A year ago, we had about 30% of connections already contained an SCT. What you can see here is that most of these contain the SCT in the certificate, though there is also a significant amount of cases where the SCT was sent via the TLS extension. OCSP is a little bit rare, as I already said. What's interesting is who chooses to send the SCT in a TLS extension. At least last year, this was mostly Google, and I think there might have been another big site that does that. We assume that Google chooses to do this because if you send the signed certificate timestamp as a TLS extension, you can basically choose if you send it or if you don't send it. So if you have a mobile client connecting to your site and the mobile client does not send the I support signed SCT extension in the connection, you can just skip sending the few 100 bytes of data, and they are not contained in the certificate either, which might make your handshake a little bit faster. On the other hand, if your client supports it, you can tag it on into the handshake and just send the data, and you don't really lose anything. We redid this measurement too a few months ago, and what's kind of interesting is that this actually hasn't changed all that much. It's about 32% of connections now that contain an SCT, but it's still not massively more. We expect this to change rather quickly because our measurement was done basically when the Chrome changes started to go into effect, but they don't go into effect for old certificates, only for new ones. So the certificates have to first time out for us to see big changes. In any case, how does this look like in practice? So if you are using Google Chrome and go into a development mode, you can see the certificate transparency proofs that are transferred here on the right. So in this case, we have a certificate that has a bunch of valid proofs, both in the certificate and sent via the TLS extension. This is another case that we found for our paper in which two SCTs were sent in the TLS extension, and both of them were invalid. And while we did our measurement, again in 2017, we found 105 certificates for which this exact case happened, that we got an invalid proofs sent by the TLS extension, and 91 of them were issued by Let's Encrypt. And while we don't exactly know why this happens, we have a suspicion, and our suspicion is that back then Let's Encrypt wasn't quite that widely used as today, and we assume that this is early adopters that are actually interested in security. Back then, Let's Encrypt did not automatically submit the certificates to certificate transparency. Those people wanted to try certificate transparency. So what you do is that you set it up yourself. You send your certificate to a certificate transparency log server, get back the signature, put that into your web server configuration so that it sends the SCT back to the browser. And then after 3 months, you have to change out your certificate. And at that point, it's easy to forget to update the configuration of your web server, and you send outdated proofs. We also found one certificate back then that embedded an invalid signature in the certificate by bypass. We contacted them back then, and I'm blanking on what exactly happened. It was one of their, yes, what they did in their case is that they issued a certificate for FHI.NO, and for some reason something went wrong during the issuance process, and they didn't actually give the certificate to the to the people. And then they issued a second certificate and included the proof for the first certificate that they generated. So the timestamps or something like that were different between the pre-certificate and the final certificate. We redid this measurement for the paper that's going to be talked about tomorrow. And this year found 16 more certificates where invalid signatures were embedded into the certificates by 4 different CAs. I think it's kind of interesting why that happened in each case, because in each case it was a different reason, but they all kind of are similar. So one of the CAs was Telia Sonera. In their case, it was a test certificate on one of their test servers that they had set up. And what happened is that like a year ago, they created a certificate transparency test certificate before they started giving those to customers. And then after a year, they renewed the certificate. And when they renewed the certificate, they did not remove the old SCT extension before they submitted the certificate to the log server. And the log server created a signature that also included the old SCT, which obviously you don't have when validating the new certificate. GlobalSign had a few certificates. In their case, it was if you included IPs in the SNI, the ordering between pre-certificate and final certificate was different, and it thus couldn't be validated. DTrust had TLS extension ordering differences between the pre-certificate and the final certificate. And Netlog, a Hungarian CA, actually had a few random fields being different. But that being said, at this point, there were basically millions and millions of certificates that were issued that did all of this correctly. And all of these were kind of extraordinary cases that we did not see very often. So from our point of view, the deployment actually worked very good, and there were just a handful of special cases. We contacted the CAs and they replaced all of the affected certificates. So in our paper, we also took a look at log operators, both active and passive. This, again, is the data set of a year ago, especially both the active and the passive side look a little bit different now. Like the Symantec log and passive traffic is, I think, at like 50%, and the Google logs are also a little bit low, and it's more distributed because there are more different logs now. One thing that we also found last year that was kind of interesting was this kind of certificate that was back then issued to transponder.amazon.com. I don't think that exists anymore. What they did is that Symantec, I think, had an interesting idea. So one of the problems of certificate transparency in some people's eyes is that it makes the certificates public. That means that all the host names that the certificates are valid for are also public. And there are apparently a few people that back then wanted to hide those host names from public, and Symantec came up with a way of basically putting instead of putting the full host name into the pre-certificate, they put, I think, a question mark into the pre-certificate and put out a document that basically said that you should expand that and just accept any domain, which I don't think any browser recognized. And we found an actual number of those certificates during our scans. And if you tried accessing them back then in Chrome, you got this nice certificate transparency required error message, because Chrome already enforced certificate transparency for Symantec back then. We also found another really interesting thing. So this is one certificate that we counted during our passive measurement on the wire. And what you can see down here is when you pass this certificate with OpenSSL, it says CT pre-certificate SCT, and then it says random string goes here. So the first thing that I thought when I read this is, okay, great, someone didn't implement this in OpenSSL. So let's look at the actual data. And the actual data is all the extensions are encoded as an octet string. And if you decode that octet string manually, you see that actually the certificate really contains an UTF-8 string that just states random string goes here. So for comparison, this is how it is supposed to look like. The interesting question is why? So this took a little bit of digging, and we actually never found out the entire reason. But basically, this certificate claims to be a certificate that's valid for CloudFront.net. We found similar ones for Twitter.net, Twitter.com. I think we found like 300 something for CloudFront and like 60 for Twitter. And those were not valid certificates. So this certificate was not actually signed by Symantec. It was just an exact clone of a real certificate that was issued to CloudFront. So someone copied the serial number, issuer, subject, and all the extensions besides the pre-certificate, the certificate transparency extensions, which they apparently couldn't handle and just were too lazy to do anything about. And I assume this was to sidestep firewalls and network monitoring devices, because if you don't perform certificate validation, this looks exactly like a CloudFront certificate. And the connections also didn't go to CloudFront. The connections went to some servers in cloud hosters in Africa, if I remember it correctly. So I think someone really wanted to hide for reasons that we were not able to determine. So we also looked at other things besides certificate transparency. We looked at HSTS and HPKP. Back then, we found that HSTS was used by about 3.5% of domains, and most people that used it correctly. There were a few misspellings. HPKP was used by not that many people, just over 6,000 with 41 misconfigurations. SCSV, so the fallback cipher suite, which is automatically deployed when your software supports it, was used by more than 96% of connections. And the reason that it was only 96% is that IIS doesn't support it, or didn't back then. So one of the interesting things we did in our paper is that we basically looked at all of these different security mechanisms, and we analyzed them looking at the effort it takes for the end user to deploy a mechanism and availability risk. And one of the things that we noticed is that, unsurprisingly, things with low effort or no effort in best case are deployed kind of quickly and kind of commonly. And the other thing that we noticed is that things that have higher risk also tend to be deployed less often than things that have lower risk. And as you can see, so things like the SCSV have basically no effort and no risk. Certificate transparency via X59 also has no effort on the user side. The certificate authorities have to do something, and no availability risk, and those are deployed quite widely. HSTS also has relatively low effort and relatively low risk, and we still see kind of big deployment. The thing that gets interesting is, for example, HPKP, which has high effort and relatively high availability risk. And relatively shortly after our paper was published, actually Chrome announced, or Chrome announced, that they intend to deprecate and remove public key pinning support, which I think they're going to switch off in Chrome 72, which at the moment is in the Canary build and will be released in a few months. So this basically supports our thesis that we had in the paper, that if you want to design a protocol or something that someone should actually use in the end, it's kind of neat if you make it a low effort and if possible also low risk, but if you can't have it low effort, at least try to keep the risk of using it relatively low if you want it to see being deployed. We also had a bunch of community contributions in our paper. So one of the fun things that we did is, as I mentioned at the beginning, we had a shared pipeline between active scans and passive scans, and we actually put the PCAPs online. So if you're interested in a PCAP of a scan of 193 million domains, you can go to the URL that is on this slide and download it. It's a little bit big. We also published the active scan results, we published the database dumps of certificate transparency that we use, and we published the analysis scripts that we used for the paper, and also the software that was used to do this. Okay, and now I'm going to talk a little bit about follow-up work that was done later. So this is a new paper that was published at the Internet Measurement Conference 2018, so just a few days ago. And that will be talked about again tomorrow. I'm actually not going to talk very much about it. I'm just going to talk about things that have a tiny bit to do with what I talked about already. One of the fun things that we did in that paper is we created a honeypot for certificate transparency. What that means is we were interested, if you put a certificate into certificate transparency with a random host name that no one could ever guess, how long do you think it takes till someone connects to the domain? The answer is between 33 seconds and 3 minutes. So people are watching this and do try to connect to you afterwards, and you get requests from kind of a lot of people. And another fun result that we got is that now that you have a list of all domain names, you can look how many people try to phish common domains, like for example, Apple, for which we found like 63,000 phishing domains. And if you're interested in more results of that paper, go to the session tomorrow. Another thing that I wanted to talk about a little bit is the ICSI SSL notary. So one of the reasons I have been doing a lot of SSL research over the last few years, and one of the reasons that this paper was possible is that back in 2011, we started a project where we were interested in how SSL is actually being used on the internet. And what we did back then is that we started a measurement effort with several universities, mostly in North America, that give us information about their outgoing SSL sessions. So basically all of these people are using a network monitoring software that is actually just changed name and is now called Seek. Back then it was called Bro. And we give them a little script that generates information about every single TLS session that's outgoing from the network, and they send that to us for storage and data evaluations. To talk a little bit about the network monitoring software, if you have not heard about it, Seek is an open source network monitoring software that basically looks at network traffic, has a few protocol analyzer, converts the network traffic into events that are completely policy neutral, and then you have scripts that you can write into a domain-specific scripting language, and it also ships with a standard library, and you can do stuff like intrusion detection, vulnerability management, final analysis, or in our case, traffic measurement for research. And this has been a research project from the very beginning. So this was started in 1995 by Vern Paxson at the Lawrence Berkeley National Laboratory. And a number of academic publications came out of it. And it has been financed by a lot of NSF grants over the years. And the way in which we use it, if you have like the SSL handshake here, is that Bro gives you events about all of the different SSL messages that you get, and we basically attach to those events and harvest information and then output one log line for each connection that we see. And Bro nowadays handles a whole bunch of the different TLS extensions that we actually see being used in practice. So back to the notary. This has been running since the end of 2011. And then at the beginning of 2012, when we started to look at the measurement data, we noticed that there were some bugs in the software and that we were doing things wrong. So we threw away everything and started the measurement again in February of 2012. And it has been going on since then. And what we are collecting are things like the cipher suites that are sent by the client, the cipher suites that are selected, if the connection is successfully established, the extensions that both server and client support, and the exact content of some of the extensions and the certificates if you're speaking TLS smaller 1.3 and so on. So we collect basically a whole bit of bunch of information that we think is interesting. On the other hand, we try to make this, we try to respect the people's privacy, so we are not really interested where a specific person is surfing to, and because of that, we don't keep client IP addresses. We keep hashes that are sorted that allow us to tell when the same client is connecting to the same server, so that we can see how effective session resumption is, but we cannot see when the same client connects to different servers over time. So this is a graph that shows the amount of connections that we get. So basically we get a few million connections per hour by our different sites. At the moment we are at a little bit of 300 billion total connections that we have observed. We have more than 45 million certificates now. Those jumps that you see in the graph mostly are people at one of our contributing institutions that do an active scan of the internet, which then also shows up in our data. And also in the last few months, the amount of new certificates that we see generally seems to have increased. So now that I've told you about the notary, let me tell you a little bit more about another research project that was also presented at IMC this year that basically uses this data set and takes a look at how TLS changed over the last 5 years. And I'm not really going to go into too much depth about this, but if you're interested, then look at the paper. And this was done together with people at India, Stony Brook University, and the Royal Holloway University of London. And what we did for this paper is basically, the big idea was that there have been a lot of SSL attacks since 2011, and we were interested, did the publication of these attacks actually cause changes in the ecosystem? So after an attack became public or was published in academia, did internet traffic actually change in any significant way? And one of the fun things that we looked at is how do the negotiated SSL versions change over time? And this graph just plots the TLS versions that we see finally being negotiated from SSL version 2 to TLS version 1.2 over time. And what you might notice here is that when we began our measurement, TLS 1.0 already was the most commonly used TLS version. However, what you might be aware of is that our measurement only started in 2012. And back then, TLS 1.2 already had been standardized for 5 years. So TLS 1.2 was standardized in 2008. And TLS 1.1 had been standardized for 7 years or so. So TLS 1.1 was standardized in 2006. And TLS 1.2 only managed to cross the threshold of being used more than TLS 1.0 in mid-2014, I think, or towards the end of 2014. And while we see a small spike of TLS 1.1, it was never really used all that much, and it was only used for a short period of time. One reason for that is that I think a lot of software, especially OpenSSL, jumped from supporting 1.0 to supporting everything up to 1.2 without the intermediate steps. So there was, I think, no version that supported 1.1 and not 1.2. Another interesting thing that changed a little bit over time is the amount of export, anonymous, and null cipher connections that were advertised over time. So back in 2012, a lot of people were advertising, especially export ciphers. And export ciphers were not really necessary anymore since the mid-90s, if I remember it correctly. And I assume that a lot of people did that because of the defaults of their software and didn't actually really want to advertise export ciphers and clients to be able to choose export ciphers. And this has become better, but as you can see, the progress was kind of very incremental and it took a while. Null ciphers are also kind of interesting, though in our case, for the networks that we are monitoring, there are actual kind of useful uses for null ciphers. One of the reasons why we still see them used a little bit is that they traditionally are used for grid FTP connections, because grid FTP connections are big data transfers of scientific data, where the scientific data is not really private, but you want to authenticate yourself to the other node that you're sending data to, so you use authenticated TLS with a null cipher. Another one that I really, really liked is this one. So this is negotiated static RSA versus forward secret connection types. So Diffie-Hellman and ephemeral Diffie-Hellman and ephemeral EC Diffie-Hellman. And what you kind of can see is that there's this one line in 2013 from which it seems like people stopped using static key RSA that much, or that was a slow but significant decline over time till 2016. And what happened then was that Edward Snowden came out with his revelations. So we are just observing what is happening, and we obviously cannot say that that caused this change, but it's at least kind of peculiar timing. And in the paper, we did a whole bunch more studies where we looked at exactly which ciphers changed how, like, for example, RC4, or how authenticated encryption is used, how much authenticated encryption is used. And if you're interested, read the paper. And I also wanted to give a little bit of information about TLS103 use. So I don't actually have all too much about that, but we basically implemented support for TLS103 relatively early on. And I have a few statistics that are kind of current on how it's being used at the moment. So the first one is connections where we basically see the client supporting it, in this case measured by the client sending the supported versions extension. I have not actually looked into the extension for this measurement. We have that data, but it's a little bit hard to access at the moment because of the way our database is organized. But basically what you can see is that the moment that Chrome pushed out the update that enabled TLS103 for everyone, which was in March, I think, TLS103 for everyone, you get up to 35% of outgoing connections that we see that signal support for it. On the server side, things are a tiny bit different, but we also see something between 4 and 5% of connections that send the extension on the server side, which probably means that they negotiated TLS103 at the end. Okay, and with that, I'm actually kind of at the end. So to give a summary mostly about the paper, we found out that deployment status correlates with configuration effort, with the risk of deploying something, and that if you make something the default, it's commonly deployed most widely. One of the things that I actually forgot to mention earlier is we did all of our measurements from several sites. So we had active scans from 2 sites and passive scans from 3 sites. And in this case, that actually didn't help us much because we basically found out afterwards that there are tiny differences, but nothing significant. And if you want to dig in what exactly is different, you typically come to the point in the end where there's a CDN or something, and for some reason it served up slightly different results for that one domain while you were scanning. And so in our case, doing distributed measurements from several sites made the effort like 3 times as high as it would have been just doing it from one side, and did not really get us any more results besides being able to say, yes, it looks the same from everywhere. And with that, I think I'm open for questions.
Hi, my name is Ashutosh Singh. So my question is, did you also have two questions actually? One is this reflective of only North America or across geographies? Do you think there will be a difference? And the second question is, did you also look into the certificate types and the key sizes, whether EC certs are picking up, and if RSA is still more popular, then what are the key sizes? If you have some comparisons.
So this is mostly North America. We have some people contributing from outside North America, but I'm not at liberty to say from where, because the sites that contribute data to us want to stay private, but nearly all of our data is from North America. So I cannot say how, if it will be significantly different if you get it like in Asia. And to the certificate sizes, we could look that up. I admittedly have not looked in recent memory. Like when I looked a year ago, nearly everything was RSA still.
My name is Ulrich Wisser from IS. You presented three ways of basically showing a SCT proof.
Yep.
Yes. As I understand, they are not mutually exclusive.
No, you can do them simultaneously.
Yes. Have you any data on how many do several ways or all ways?
Actually, yes, we have. The problem is that I don't quite remember the numbers, and I will have you look in the papers. So from what I remember, it's kind of unusual that sites do both simultaneously. At least it was in 2017. And if they do it simultaneously, it's typically via the TLS extension and via the certificate. There were like 2 cases in which OCSP was used simultaneously with something else.
Wes Hardiker, ISI. Fantastic work. This is great to see. My immediate reaction is, okay, well, how can we translate this into helping deployment? And you've answered some of that as well. Did you look at, so now switching to the question side, did you look at other usages of TLS besides web? Did you look for certificates in other places?
So the answer is yes, we do. So our measurement, so basically how the network monitoring system works is that we attach ourselves to a few ports like 443 that are well known to speak TLS. In addition to that, we basically have a regular expression that we match to the beginning of every connection that should be able to catch all TLS connections. And when that regular expression matches the beginning of a connection, that basically tries like, does this look like a client hello or a, there was something else that you can send at the beginning of a connection if you really want to. Then it just shoves it to the TLS analyzer, and the TLS analyzer tries to parse it and either says, yes, this is TLS, or fails away. And we actually have written papers about TLS on other ports. There was one paper at NESS, I think 2 years ago, where we looked at TLS for communication protocols like email, XMPP, and so on. Back then, deployment was worse there than for HTTPS.
Okay. You may want to talk to Victor Duchovny from 2 Sigma, who does a Dane survey for mail in particular, and has a large quantity of, he's trolled large parts of the internet looking for TLS on the email side, and he has a large number of hosts that you may want to query and pull down their certificates for. I can put you in touch with him later if you want. He and I actually jointly publish a website, stats.danosec-tools.org, that actually lists Dane usage and shows the upward graphs of that. And I suspect that you can pull in a lot more data by talking to him.
Okay.
Christian Wittemer. I like these measurements, and I like the idea that you can measure deployment from traffic.
Yes.
Don't you have a small problem with TLS 1.3?
Again, please, I just didn't quite get.
A lot of the data that you analyze were sent in clear text in the server flight in TLS 1.2 and below, and they are encrypted in TLS 1.3.
Yes. I obviously am personally a little bit sad about that because it makes my work for doing these measurements more difficult. But I understand why this is being done. And I basically take this as an opportunity because we see the on-ramp of a new version of the protocol.
Yeah.
And we also get to see all the stragglers over time and who doesn't update. So it's kind of interesting still.
Okay.
And speaking about that, one thing that I forgot, they're actually already looking at the data of the beginning, like when TLS1.3 was experimental, is kind of fun because you have that supported versions extension. And from my point of view, it's kind of interesting what everyone sticks in there. Because while there are the obvious draft values, like I support TLS1.3 draft 28 or something like that, Google had their own values that they used. I think they started with 1E and they used it for stuff that was kind of TLS1.3, but not really. And I suspect Facebook also had some because we saw a bunch of them started with FB. I didn't actually look if the connections terminated with Facebook, but that's always a good guess. So you still see interesting things.
Hi, Anshul Malhotra. My question is, it's maybe I just missed something in the presentation, but what is the risk factors here in the deployments that the deployments
I might not have explained it more clearly enough. So the risk factors mean, for example, if you, let me go back to that. If you have something like HTTP public key pinning, if you misconfigure that to or you lose access to the key that you specify, you might lock yourself out of your own domain. So basically, web browsers might refuse to connect to your domain because the key of the certificate that you are serving doesn't match anymore and you don't have access to that anymore. And web browsers, in theory, you can set something like cache this information for a year and have a certificate on there and it works for a bit and then you lose the key and don't have access to it anymore and get a new certificate, and people that have your old PIN saved will refuse to connect to your site until that year is up. So that's high risk factor in that case. Which HSTS, it gets much more low risk because the only thing is that you need a valid certificate that's easy to get.
Yeah, Yoav Nir, a former WebSec chair. We standardized HPKP, and the thing is, once browsers record that your key should be this,
yep.
Once it's different, they're blocked, and they're blocked for months.
Yep.
And there's no way you can remedy that other than push an update to Chrome and every other browser. So that never caught on because of this.
Yep.
Yeah, this is more of a comment. I feel HPKP and CTL, the Certificate Transparency List, they are sort of competing programs. So Google decided to pick one eventually, and that's why CTL picked up and they decided to decommission HPKP. That's just my... I know. So I'm saying of the two, I think that's they picked up CTLs.
Okay, well, one more question.
Matt Ford, I was kind of surprised by your kind of final point that you didn't expect that having more diverse measurement points or vantage points would lead to sort of greater insight or more divergence. I wonder if that tells us something about the way the network is being used.
So it might. So what's generally kind of interesting is when you compare passive measurements to active measurements, because then you see a huge difference, because active measurements, basically you see everything that exists on the internet more or less. On passive measurements, you see what is being used. And one thing that you might have noticed is that we have like 45 million certificates in our active data set, in our passive data set now. What you might be aware of is that when you do a really full scan of the internet, just once at this moment, you already get more certificates. And like for the first few years when we didn't have anyone actively scanning, we were like at 2 or 3 million certificates. So the amount of sites that people actually do surf to or do access is much, much, much lower than what's actually available. So if you just do an active scan, you get a hugely skewed picture of what's going on in the internet. And what is also really interesting is like when you do an active scan of the internet, at least in the past, you found a lot of servers with not so good configurations or choosing cipher suites that are not really that great. And if you look at the passive data again, tons and tons and tons of people go to Facebook, Google, and the big CDNs, and like 80–90% of your connections use from today's point of view perfect security. And then you have a lot of weird stragglers that you partially really, when you start digging into things, you find things where you find like one connection in your data set that used a specific random type that you have never seen before. But I think you get it's from a vantage point, we have not really seen a big difference, but if you compare passive measurements with active measurements, you get a completely different different view from what is going on in the ecosystem at the moment.
Okay, well, thank you very much. Your additional talk is going to be given tomorrow during MapIG.
So I'm not going to give that. That is going to be given by Matthias.
Okay. Okay, thank you.
Thank you.
All right, blue sheets. We've got, does anybody need them, and does anybody have the other one? Okay, is there any other business?
I think I'm good.
I think we're done.
Thank you. Thank you all for coming.
Thank you. That was really interesting. I co-chair the Certificate Transparency Working Group, and so I was really interested in your comments on a couple of things. One, of course, was about the immediate action.